How's everybody doing? I know what you're excited about today. You're excited about doing linear regression. Okay, this is actually really, really cool. We talked about calculating the correlation coefficient the other day. We had our scatter plot, remember, and we had our data down below of we were tracking the population density in millions of major counties around the country, and we were comparing that against the number of COVID-19 cases in thousands. And we saw that there seemed to be, we were calculating the R value, right, which is the correlation coefficient. And if you remember the R value, when we go through that whole big long equation, all that mess, we calculated our R value, and we saw that our R value was very, very close to +1. Okay, if you remember the R value in the correlation coefficient, the R value, when it is 1 or close to 1, we can have strong confidence, great faith in our numbers that as the X, the values along X increases, as our X increases, our Y is going to increase positively corresponding to the X. Okay, so there's a correlation there. Right? As X goes up, Y goes up. Okay. Remember, if our R value is close, either at -1 or close to -1, we can have strong confidence that there is a negative relationship that's going on. In other words, as our X value increases, our Y value decreases correspondingly. Okay. That's how we calculate. That's what the R value. Remember, an R value of 0 means there's no relationship going on at all. We don't have any confidence that one thing has anything to do with the other. Okay? What we saw when we ran our populations in millions of those major counties, what we saw is that as those populations went up in millions, the COVID-19 cases went up in thousands. And there was a very strong confidence, our R value was very close to 1, that indeed that there is a relationship between those, and we justified this whole this isolation, the social distancing. We justified the idea of social distancing based on that. Okay, so what we want to do now is, what if we wanted to take those data, and what if we wanted to figure out what line, try to figure out the equation for the line that best describes all of those data points. Okay, how could we do that to create the equation for that line so that we can shoot the line off this way or down that way, and we can predict? That's the whole purpose of doing a linear regression, is once we have the equation for the line, then we can plug in whatever X and Y value, whatever X value we want, and we will get a Y value that corresponds. By producing the equation, this linear regression, or the line of best fit, by producing the equation for that, it allows us the ability to predict future conditions or conditions in other communities or things like that. That's what it allows us to do, which is why it's really important. Once we have the data from the correlation coefficient, if we see that our R value is suggesting there's a relationship going on, let's go ahead and put a line to it so that we can make predictions and hopefully save lives. In the case of this anyway, we can save lives. So let's go ahead and review a little bit about the equation for a line. The equation we're going to be working with is called the slope-intercept. The slope-intercept equation for a line. And if you remember from algebra, that is y equals mx plus b, where m is the slope of the line and b is the y-intercept. Okay? Remember the slope? The way that we described slope is we described it as rise over run. In other words, it is the change in the y value over the change in x. Or putting it another way, if we have 2 points, we simply take the difference between our y, difference between our y values, and we divide them by the difference between our x values. And that's how we get this rise over run, this change in that. The way that we get the B, what we're going to do to get B, oh, by the way, if we want to do this in terms of running on our, remember when we did our bivariate data analysis, we had all those x squareds and the x bar and the x minus the x bar and all that kind of stuff. Okay, we're going to convert this formula right here, we're going to convert it into that form, and it will look like this. This is the formula that I'm going to be using, right? We're going to take our x bar, our average of our x points, we're going to multiply them by the average of our y points. So take the average of our x in our order pairs, take an average of our x, we're going to multiply them by the average for the y, and we're going to subtract for that the average of x times y. And we are going to put all of that over the average of our x values squared. So we're going to take our x bar, this number right here, and we're going to square it, and we're going to subtract from that all of the average of our x squared. So we're going to square all of our x terms, add them up, and take the average of those, and that's going to give us this number. Notice that here we have, in a sense, our change over y. That's what's going on here, and this one represents our change over x. So statistically speaking, that is going to give us the slope of our line. To calculate using these same terms right here for our data, to calculate the b value, that's a little bit easier, our y-intercept, we simply take the the average of all of our y values, and then we subtract from that the slope times the average of our x values. Once we can calculate these two numbers, our slope and our x or y-intercept, we can then create an equation for a line of best fit that's going to allow us to use that data that we collected on the COVID-19 and how that relates to population densities. That will allow us to be able to predict that line or create that line, and then using that line to be able to predict populations of COVID-19s that might occur in other cities given certain density population or population densities. And that's why we do this. So I'm going to go ahead and get all those data points and a graph written up. So rather than bore you with that, we're going to take a brief intermission. Okay, so what I've done is I've taken 5 of our data points. Since New Orleans was an outlier, I went ahead and left it out because the issue is not to predict something about COVID-19 right now. The issue right now is we're trying to learn how to plot out linear regression. I've also taken the liberty of simplifying my data points. So I kind of rounded and just made some averages. That will allow me to make some simpler data points, and it makes the math a whole lot easier, again, for the sake of illustration. So let's go ahead and plot out this, and then we'll calculate the numbers that we need to plug into our formula for getting both the slope and the y-intercept. And once we have that, we should be able to get the equation for the line that we need. That would be the line of best fit, and that's what we're going after. So we're going to start at the top. This is Cook County, Illinois, and they had 5,011,000 cases. So their point would be about here, up and over, a little bit higher than that, about there. That's good. Good old Jeffco, Alabama. We're basically at 0.5 million and about 0.5 cases, or 500 plus cases. Again, I rounded all these numbers to make the math easy. Miami-Dade, Florida is about 2.5 million and about 6,000 cases. So that would put us about there. Good. King County, Washington was at 2 million and they were at about 4,000 cases. That puts us about there. And Fulton County, Georgia, where Atlanta is 1 million, and they have about 1.5, so about 1,500 cases. Okay? And so that gives us our data points. Again, we can see that nice line. We can set it really good. The question is what kind of a best fit? What's the equation for the line that comes through this? Okay? Remember, we're defining the best fit line as the line where each of these points is at their average least distance from that line. That's what we're looking for. Now, in order to get that, we have our equations that I had given you before about how to calculate the slope using these numbers and how to calculate the y-intercept using these numbers. So given that, what we need to figure out is we need to figure out what is the mean of our x's. We need to figure out what is the mean of our y's. We need to figure out what is the mean of our x times y. We need to figure out what is the mean of our x squareds. Those are the 4 pieces of data that we need. So to get our average for x, we would add up 5.5, 2.5, 2, and 1, divide by 5, and you would see that we would get a 2.2 value for our x, the mean of our x's. Okay? For the mean of y, do the same thing, add up our y values in those ordered pairs, and we would get 4.6 for that value. We then take and multiply 5 times 11, 0.5 times 0.5, all the way down, multiply those ordered pairs, add those together, then take the average, and we would get 15.96. 95, 15.95, and then if we take our x's, square them all, add up the x squares, and take the average, we would end up with 7.3. Okay? Once we've done that, we can then run our numbers. So our m is going to be equal to 2.2 times 4.6, subtracting from that our 15.95, dividing that by our 4.84 minus our 7.3. Okay? If you remember that 4.84, you can look back on the equation I just gave you and find out where that 4.84 came from. See if you guys can read and figure that out. If you reduce all this down, what you'll find is that our m value is very, very close to 6. I'd say approximately, I'm going to do the approximate symbols, 6 over 2.5. Again, I'm rounding for the sake of making this easy. So our slope is 6 over 2.5. What that means is that for every 6, remember slope is rise over run, so for every 6 we go up, we come up here to 6, we will go over 2.5. And you can see that is almost dead on where we're supposed to be, right there. 2.5 and 6, right? That's what we calculated, and that is almost spot on right where we're supposed to be, which is fantastic. Okay? If we want to get our y-intercept is b. I'm going to go ahead and erase these data points really quick, just to give me some room to do some math. You don't need the data anymore. Our b is going to be equal to 4.6 minus, remember the slope, times 2.2, which is our average of x. So the slope was 6 over 2.5 times 2.2. If we run this math, right, multiplying these together, 6 times 2.2, divide that by 2.5, subtract that from 4.6, and what you'll find is our y-intercept is at 0.6 or negative 0.68. So basically -7, which would put our y-intercept down here. If our y-intercept is there, and we go up 6, 1, 2, 3, 4, 5, 6. Remember, we're starting at -0.7, so we'll end up -0.7 below 6, which is 5.3, about here. We go to there and then go over 2.5. That will put us about here. And then if we go from here up again, 1, 2, 3, 4, 5, 6, that will put us about here. And we would come over to about 5, which is here. And that would put us about like that. And you can see, if I take my ruler and lay it up on that line, then that gives us, okay, pretty close. That gives us our line of best fit. We have an equation that we can now put to it. The equation would be y equals 6 over 2.5 x plus, actually minus 0.68. I'll go with minus 0.7, right? Minus 0.7. So that gives us the formula for our line of best fit. And you can see that these are on the average pretty close to where we are. So, and that is how you calculate the line of best fit.